In this question, a small disk A is placed on an inclined plane forming an angle alpha with the horizontal and is imparted an initial velocity v0 like this. Find how the velocity of the disk depends on the angle phi. This angle phi is taken from the greatest slope on this incline. Okay. If the coefficient of friction, here it is represented with k, we usually represent it with mu, but it is k here, and that is equal to tan alpha. And at the initial moment, phi naught was pi by 2, means the disk was projected like this, okay, with some speed v naught. So it will definitely change its path, and at some instant when it is making an angle phi with this greatest slope, x-axis we are calling it, how this v and phi will be related, this is what we need to find out. Okay, so to solve this question, first we need to see what all forces acting on this disk. So definitely there will be a component of its weight, and that will be along the inclined plane, and that will be mg sine alpha. Okay, this force will be in this direction, and this force will be mg sine alpha, like this. And there will be a friction, which will be kinetic friction, which will be acting opposite to the velocity at every instant, and this kinetic friction will act like this. Okay, so these two are the forces that will be responsible for changing the motion of this particle. Now let's first try to find out what is the kinetic friction acting on this disk. So this kinetic friction Fk will be equal to k into normal reaction. Usually it is mu into normal reaction. And in such situation, when the particle is placed on an inclined plane with inclination angle alpha with horizontal, the normal reaction becomes mg cos alpha. And since k is tan alpha, so we'll write tan alpha into mg cos alpha, which gives us kinetic friction as mg sin alpha. Okay, and there is a component of mg which is acting down the incline, and that is also mg sin alpha. So magnitude wise, these two forces are equal, but direction definitely will be maybe in any direction. Mg sin alpha will be always along down the inclined plane, but kinetic friction will keep on changing its direction. Okay, but magnitude will always remain mg sin alpha. Now, what all equations we can write? So let me project this thing, this inclined plane, in this plane like this, and we are calling it this as x-axis. Okay, so mg sin alpha will be acting this way. This is mg sin alpha, and suppose the disk was initially projected from this point with some speed v0, it was said in the question, and due to mg sin alpha it will change its direction, and let's say the path that it follows goes like this. Okay, and at some instant its speed is, let's say, v. This is speed, obviously velocity will be tangential to the path, and suppose this makes an angle phi with x-axis, which is the greatest slope here. Okay, now we can clearly see this kinetic friction, which is equal to mg sin alpha, will be always opposite to velocity. So this is the force mg sin alpha here, and there will be another force which will be acting down the incline like this, and this will be again mg sin alpha. All right, so we can write, since mg sin alpha is exactly opposite to its velocity, and this mg sin alpha, which is component of its weight, is at some angle with the speed, so definitely the speed will decrease, and we can write the rate of change of speed. Minus sign tells us that the speed is going to decrease, and we can write minus dv dt will be equal to this mg sin alpha upon mass is going to be g sin alpha, and there is a component of this mg sin alpha along the speed which will try to increase the speed, so we will write g sin alpha plus g sin alpha cos phi. This is very much evident here, you can see. Now we can write this simply as g sin alpha into sorry, we should put a minus sign here because we have written rate of decrease of speed. So there should be a minus sign here. Okay. Now this is g sin alpha 1 minus cos alpha. Let's call it equation number 1. In this direction, in along y direction, we can write dvx by dt, rate of change of the x component of its speed, will be equal to g sin alpha, which is trying to increase the speed, and the component of this mg sin alpha will try to reduce the x component of its speed. So we'll write g sin alpha minus g sin alpha. This angle will also be phi. So the component along x will be g sin alpha cos phi. So this then gives us g sin alpha 1 minus cos phi. This is our equation number 2. So clearly we can see here that in equation 1 and 2, right hand sides are equal, so left hand side must be equal. So equating left hand side, we get minus dv by dt will be equal to dvx by dt. So this dt will get cancelled out. So we get integral. If we integrate both sides, we get integral of minus dv will be equal to integral of dvx. Now the limit for v, the initial speed was v naught, and after a certain time, let's say it becomes v. The x component initially was 0, and at the shown instant, the x component is v cos phi. So this limit will go up to v cos phi. So if I substitute the limit, we get v naught minus v is equal to v cos phi. This then gives us v as equal to v naught divided by 1 plus cos phi. Now we can verify this result from the initial condition. If we put phi is equal to pi by 2, we'll end up getting v naught, which was the initial speed. Okay. Now they might ask you what will be the speed after a long time. So clearly after a long time, if you wait for a long time, the particle's speed velocity is going to be down the incline. Okay. And at that situation, it will attain terminal velocity because mg sin alpha and the friction is also mg sin alpha, which will be acting opposite to speed. So at that time, it will attain a constant speed, terminal speed, and when the velocity becomes along x-axis, so phi will be equal to 0. In that case, the terminal speed will become v naught by 2. So if they might ask you this question, what will be the terminal speed of the particle, and that is going to be v naught by 2, or terminal speed will be down the incline. Okay.